Okay, I think we are live now. So today we're going to start with chapter 7, the managing growing project with packages, crates and modules. So as usually, let's recap a bit what was last time. Basically it was chapter 6, section 6.2, 6.3, the match control flow and concise control flow with if let. Let's take a look. So we have enumeration and we can use match. And interesting part was, I think, that we can have can associate the state, some value to the enum. Also, we learn how to handle the option type. Option basically mean that we have some value or there is no value, and it's replacement for the null concept in other languages. Cool feature. Matches are exhaustive, so we always should cover all cases if we do match. But we also can use like few and then say for all other cases we do something like this, but we should do it explicitly. And also there is underscore placeholder if we don't need the value, we can just just use underscore here. And if let is basically alternative, so if we want to match only one case or one case and then else for everything else, this is also possible. We also here destructuring the state or associated value with enum case. Yeah, basically this is it, and I think we can now start with chapter 7. This is something about splitting the code into different files. For this moment, like, we stay all the time in our main file, main rs, basically everything we need so far, but of course in real world we will need more complicated structure. So today we started learning it, and so let's start reading the book actually. As you write large programs, organizing your code will become increasingly important. By grouping related functionality and separating code with distinct features, you'll clarify where to find code that implements a particular feature and where to go to change how a feature works. Okay, yeah, exactly what we talk about just now. The programs we've written so far have been in one module in one file. As a project grows, you should organize code by splitting it into multiple modules and then multiple files. A package can contain multiple binary crates and optionally one library crate. As the package grows, you can extract parts into separate crates that become external dependency. This chapter covers all this chapter covers all those techniques. For every large project comprising a set of interrelated packages that involves together, Cargo provides workspaces, which we will cover in the Cargo Workspaces section in chapter 14. Yeah, chapter 14 will be at some point in future. Right now we're on chapter 7, but doing good progress. So yeah, basically intro says what we are taught, that bigger project we need more complicated structure. We'll also discuss encapsulated implementation details, which let you reuse code at high level. Once you implemented an operation, other code can call your code via its public interface without having to know how the implementation works. The way you write code defines which part are public for other code to use and which part are private implementation details that you reserve the right to change. This is another way to limit the amount of details you have to keep in your head. So yeah, encapsulating, interesting topic, interesting to see how it will work in Rust, because I'm already like through first 6 chapters. I already find some unique concepts about the Rust language, so this is interesting. A related concept is scope. The nested context in which code is written has a set of names that are defined as in scope. When reading, writing, and compiling code, programmers and compilers need to know whether a particular name at a particular spot refers to a variable, function, struct, enum, module, constant, or other item, and what that item means. You can create scopes and change which name are in or out of scope. You can have 2 items with the same name in the same scope. Tools are available to resolve name conflicts. Yeah, scope is definitely an important topic in each language, so we'll learn about it. Also curious. Rust has a number of features that allow you to manage your code organization, including which details are exposed, which details are private, and what name are in each scope in your programs. These features, sometimes collectively referred to as the module system, include packages, a cargo feature that let you build, test, and share crates, crates, a tree of modules that produce a library or executable. Modules and use let you control the organization, scope, and privacy and passes. Pass, a way of naming an item such as struct, function, or module. Yeah, really important topics here. In this chapter, we'll cover all these features, discuss how they interact, and explain how to use them to manage scope. By the end, you should have a solid understanding of the module system and be able to work with code like a pro. Okay, so basically the intro here is done, and can jump on something more specific, and this is section 7.1, packages and crates. The first part of the module system will cover packages and crates. A crate is the smallest amount of code that Rust compile consider at a time, even if you run rust.rc rather than cargo and pass single source code file, as we did all the way back in the writing and running Rust program section of chapter 1. The compiler considered that file to be a crate. Crates can contain modules, and the modules may be defined in other files that get compiled with crate, as well as we'll see in the comment section. So basically we have crate, which is it's kind of a program. It's everything we compile it and then run. It's one crate. Smallest amount. Then crate can contain modules and etc. Okay. A crate can come in one of two forms: a binary crate or a library crate. Binary crates are programs you can compile to an executable that you can run, such as command line program or a server. Each must have function called main that defines what happens when the executable runs. All the crates we've created so far have been binary crates. So if we quickly back to our code, we have main rc file and we have function main. Exactly what was told, each must have function called main. This is what we have in our test code. And when we do cargo run, it compiles into a binary and run it. Basically, we can find in target debug folder our binary is in num6, I think. Okay, this is kind of clear. Library crates, yeah, this is something we don't touch a lot yet. Library crates don't have a main function and they don't compile to an executable. Instead, they define functionality intended to be shared with multiple projects. For example, the ren crate we used in chapter 2 provided functionality that generates random numbers. Most of the time when Rusticians say crate, they mean library crate, and they use crate interchangeably with the general programming concept of a library. So yeah, I have this confusion a bit that I heard this crate, and this is kind of meant library for me, but actually there is two type of crates: the library one and the binary crates. This is kind of clear, so move forward. The crate root is source file that that the Rust compiler starts from and makes up the root module of your crate. We'll explain modules in depth in the defining modules to control scope and privacy section. This is actually next section. Okay. A package is a bundle of one or more crates that provides a set of functionality. A package contains a package. Okay, package is several crates. One or more crates, right? Set of functionality. A package contains a cargo toml file that describes how to build those crates. So we have cargo toml. We can take a look. And you see we have, there is package, there is the name of the package, and I believe in dependency we can place library crates. So right now it's like one binary crates, but we can attach library crates and it will be exactly what it says, a bundle of one or more crates. Okay. Package contains a cargo toml that describes how to build those crates. Cargo is actually a package that contains the binary crate for the command line tool you've been using to build your code. Cargo is actually a package. Okay. The cargo package also contains a library crate that the binary crate depends on. Other projects can depend on the cargo library crate to use the same logic the cargo command line tool uses. This is interesting because so far from I read, it says binary place like compile code into like where it was the crate. So binary crate, it's compiled and placed into binary, and the library crates don't compile to an executable. So I have some confusion here. So if we add some library, we still need it in our binary, I guess. So maybe when it's part of the package and the binary and our binary crate requires it, it become a part of the program. I guess this is how it works. But when we just if it's just a library, like we created a library and we don't include it anywhere, there is no like we don't compile it into binary, so we not going to include this binary in our programs. We won't include the source code or something like this. Okay. So let's back where we stopped. A package can contain as many binary crates as you like, but at most only one library crate. As many binary crates as you like, okay, but at most only one library crate. So in case, yeah, it's not super clear statement actually for now for me. A package must contain at least one crate, whether that's a library or binary crate. Yeah, this is kind of clear. Let's walk through what happens when we create a package. First we enter the command cargo new. So cargo new, my project, cargo toml, src, and main rs. Yeah, this is what we have here. Main rc and cargo toml. This is what we have. After we run cargo new, we use ls to see what cargo creates. In the project directory, there is a cargo toml file giving us a package. There is also a src directory that contains main rs. Open cargo toml in your text editor and note there is no mention of src main rc. Cargo follows convention that src main rc is the crate root of binary crate with the same name as the package. Likewise, cargo note that if the package directory contains src librc, the package contains a library crate with the same name as the package, and src librc is its crate root. Okay. Cargo passes the crate root files to rastrc to build the library or binary. So this is default for library, this is for binary, and usually if we have package with library, it will be one library. We read it somewhere about, but we can have many binary crates, entry points, as I understand. I guess there was a project yeah, Spotify Rust. Just would like to check some example. So we have cargo toml here. There is a package Spotify TUI. Have different dependencies here, and in src we don't have yeah, we have main rc, but I wonder, is there a library? So far I don't see librc. Okay, maybe this is not example I was looking for. Let's just back to our book. So here we have a package that only contains src minor c, meaning it only contains a binary crate named my project. If a package contains src minor c and src librc, it has two crates, a library and a binary and a library, both with same name as the package. A package can have multiple binary crates by placing files in the src bin directory. each file will be a separate binary crate. Let's look at it here. Do we have bin? I don't think so. Okay, I think we will find out about it later. So let's continue with 7.2 section. Defining modules to control scope and privacy. So we just learned about a bit packages and crates, but just in theory. We haven't done anything in practice. So let's quickly recap the package. We have the name and binary will be created. We have binary crate here, which by default may name main RC with main function, and the binary will be called exactly as package. And you see it in the target debug. There is a binary in ARM6 with the name exactly as we have in TAML and ARM6. Okay. So now defining modules. In this section, we'll talk about modules and other parts of the module system, namely classes that allow you to name items, the use keyword that brings a pass into scope, and the pub keyword to make items public. We'll also discuss the as keyword, external packages, and the globe operator. Okay, this is definitely something more practical now. First, we are going to start with a list of rules for each reference when you're organizing your code in the future. Then we'll explain each of the rules in detail. Okay. Modules cheat sheet. Here we provide a quick reference on how modules passes the use keyword and the pub keyword work in the compiler, and how most developers organize their code. I'm going through example of each of these rules throughout in this chapter, but this is a great place to refer to as a reminder of how modules work. Start from the crate root. Okay, when compiling a crate, the compiler first looks in the crate root file, usually src-libRC for a library crate or src main rc for a binary crate for code to compile. So the word usually means for me that we can explicitly specify in somewhere, probably in cargo toml, what is the root, what is the crate root file. If we don't specify it explicitly, then it is src-libRC or src main rc. Yeah. So declaring modules. In the crate root file, you can declare new modules. So you declare a garden module with mod garden. The compiler will look for the modules code in these places in line within curly brackets that replace the semicolon following mod garden. In the files src garden rc, in the files src garden mod rc. So far I don't actually get it. Is it Okay, declare a garden. So garden is just a name. It can be anything. So if we want to declare a module called garden, we do mod garden and semicolon. The compiler will look for the module's code in these places, in line within curly bracket that replace the semicolon following mod garden. So if here we have curly brackets and some implementation, that will be code of this module. In the file src garden rc, okay, and in the file src garden mod rc. Yeah, now makes sense. Like if it's something part of the file, we just do it in line. Then if something bigger and we want to place it into a separate folder, we place it in src garden rc. If it might be contain more files, I guess we create separate folder for it, a garden, and the root of the model will be mod rc. Okay. Declaring submodules. In any file other than create root, you can declare submodules. For example, you might declare mod vegetables in the src garden rc. The compiler will look for the submodule code within the directory named for the parent module in these places. Inline directly following mod vegetables within curly brackets instead of semicolon. Yeah, this is same as for modules. In the file src garden vegetables rc, in the, so basically same, but it will be not in src but in garden directory in this case. Okay. Passes to code in module. Once a module is a part of crate, you can refer to code in that module from anywhere else in the same crate, as long as the privacy rules allow. Using the pass to the code. Okay, so we can use anywhere same crate using pass to the code, but there could be some privacy restriction. For example, an asparagus type in the garden vegetables module would be found at crate garden vegetables asparagus. So yeah, we have like clear structure here. There is module, submodule, submodule, pass, and it starts with crate. Private with public. Code within a module is private for its parent modules by default. To make a module public, declare it with a pub mod instead of mod. To make it within a public module, public as well, use pub before their declaration. Yeah, basically for think this is clever way. By default we have private everything, and only when we want to use something out, provide something outside, we explicitly declare it is public with pub keyword. This is completely makes sense to me. The use keyword within a scope. The use keyword creates shortcuts to items to reduce repetition of long paths. In any scope that can refer to create garden vegetables asparagus, you can create a shortcut with use. Okay, and from then on you only need to write asparagus to make use of that type in the scope. Yeah, this makes sense to me. So we do some kind of import, some command keyword, and I think in C++ you also have use. C++ use namespace. Oh, it's using. Yeah, but still, like we're doing using namespace std, and then we can drop std and have directly access to the cout and L and L, yeah, something like this. Otherwise we need to type like std cout or std and L instead. So yeah, use keyword completely makes sense to me. Here we create a binary crate named backyard that illustrate these rules. The crate directory, also named backyard, contain these files and directories. I think we want to create something like this to try it ourselves. So yeah, let's create new package, cargo new backyard, go to backyard, open it with new vim. We have main RC, now we can create garden RC. And also vegetables RC in the yeah, add garden slash vegetables RC. And I think that's it. Now we'll want to declare our garden module. So we're going here and we do pub mod garden, so it will be public. We're using here vegetables asparagus, but we don't really create it yet, so maybe let's go to the vegetables, maybe in garden even. Yeah, you see src garden rc, you need to declare pub mod vegetables. And here pub mod vegetables mean the code in vegetable C is included too. That code is okay. And here we just create a struct which will be derive debug as Copilot suggested us. Then pub struct vegetable. Something like this for now. And now we can back to our main and we can use create garden lsp, yeah, vegetables, and yeah, it was asparagus originally, so let's asparagus. Okay, we have asparagus and let plant, we create struct and our plant is cargo run. And it works. Cool. Yeah, we have quite non-trivial structure now. This is cool. And kind of straightforward, maybe for someone who new to programming it would be not such obvious, but yeah, if you have some experience, it shouldn't be that bad. So now let's go into detail of these rules and demonstrate them in action. Yeah, this is what we need. A bit of examples and practice. Let me have a sip of water. So grouping related code in modules. Modules let us organize code within a crate for readability and easy reuse. Modules also allow us to control the privacy of items because code within a module is private by default. Private items are internal implementation details not available for outside use. We can choose to make modules and the items within them public, which expose them to allow external code to use and depend on them. All right. Yeah, basically I guess this is what was called encapsulation. We can do some different implementation details, which is private, we can change them, but public items should stay compatible for external use. In case we provide modules to someone else. Of course, if we just consume our modules ourselves, we can change it if we don't have this backward compatibility issue. Okay, as an example, let's write a library crate that provides the functionality of a restaurant. We'll define the signature of functions, but leave their bodies empty to concentrate on the organization of the code rather than implementation of the restaurant. Okay. In the restaurant industry, some part of the restaurants are referred to as front of house and others as a back of house. Front of house is where customers are. This encompasses where the hosts seat customers, servers takes orders and payment, and bartenders make drinks. Back of house is where the chefs and cooks work in the kitchen. Dishwashers clean up and managers do administrative work. Yeah, so front is something that visible for everyone. The back is visible only for people who work in the restaurant and they know what's going on inside as well. To structure our crate in this way, we can organize its functions into nested modules. Create a new library named restaurant by running cargo new restaurant and --lib, and then enter the code in the listing 7.1 into librc to define some modules and function signatures here in the front of house section. Okay, let's start. So cargo new restaurant lib. And oh, sorry, I go to the wrong place. I was curious why I don't have librc, but it's the old project rectangles, not the restaurant. Oh yeah, I write it wrong. It's not carge, it's cargo. Now we're in the right place, and there is librc, which is what we expect. Oh, nice, there is some tests already. Test is something I'm curious about. But maybe we will learn a bit later about it. Anyway, let's back to our listing and just copy paste this. Where should we paste it actually? I guess in librc, because it defined front of house. We defined a module with the mod keyword followed by the name of the module, in this case front of house. The body of the module then goes inside curly bracket. Inside modules we can place other modules, as in this case with the module hosting and serving. Yeah, here's hosting and serving. So okay, modules can also hold definitions for other items such as structs, enums, constructs, traits, and as in listing 7.1, functions. Yeah, we have definition of the functions here. By using modules, we can group related definitions together and name why they're related. Programmers using this code can navigate the code based on the groups rather than having to read through all the definitions, making it easier to find the definitions relevant to them. Programmers adding new functionality to this code would know where to place the code to keep the program organized. Yeah, makes sense. So if you looking for the functions, methods related to the hosting, it's grouped by hosting. And if we have just list of all functions without these groups, it will be much harder to find it. Maybe not in this simple example, but in average library there is a lot of different methods. So completely makes sense to me. Okay. Earlier we mentioned that src mainrc and src librc are called creates roots. The reason for their name is that the contents of either of those two files form a module named create at the root of the create module structure, known as module tree. So this is, I guess, when we wrote use create colon colon, the create is exactly this root create module. Okay. Yeah, this is how this is the path we can access to the method. Something like create oh, it should be pub to be available actually. So cargo build. No, it's not work like this, but and let's also remove our pops. Keyword. So this tree shows how some of the models nest inside one another. For example, hosting nest inside the front of house. The tree also shows that some models are sibling to each other, meaning they defined in the same model. Hosting and serving are sibling defined within front of the house. If model A is contained inside model B, we say the model A is the child of model B and that model B is the parent of model A. Notice that the entire model tree is rooted under the implicit model name crate. So crate is a root module. Okay. I think we are good here, and we can try to read this section today as well. 7.3 passes for referring to an item in the module tree. Okay. To show Rust where to find an item in a module tree, we use a pass in the same way we use a pass when navigating a file system. To call a function, we need to know its pass. A pass can take two forms. An absolute pass is the full pass starting from a crate root for code from external crate. The absolute pass begins with the crate name, and for code from the current crate, it starts with a literal crate. Okay. So yeah, crate root module, and then 111. A relative pass. Start from the current module and use self, super, or identifier in the current module. This is interesting. I'd like to see example. Both absolute and relative passes are followed by one or more identifiers separated by double colons. Returning to list in 7.1, say we want to call the add to waitlist function. This is the same as asking what the pass of the add to waitlist function. Oh, I see what I just write it wrong. Great. No. Okay. Say we want to call add to waitlist function. This is the same as asking what the pass. Oh, I removed also the pub. What if I no? It still says I'm doing it wrong. but yeah, always want to experiment how things works. This is the same as asking what the path of the add to wait function. Listing 7.3 contains listing 7.1 with some of the model and function removed. We'll show two ways to call the add to waitlist function from a new function eat at restaurant defined in the create route. These paths are correct, but there is another problem remaining that will prevent this example from compiling as is. We'll explain it why in a bit. The eat at restaurant function is a part of our library creates public API, so we mark it with the pub keyword in the exposing path with the pub keyword section. Okay, it will be later here. We'll go into more details about pub. Okay, in the different section we will see, but let's try this code. So why it wasn't working? Should I place it inside of function or something like this? So create, yeah, because it was not in function scope. So if we do cargo build, no errors anymore. Okay. Yeah, I was close. Okay, we also can use relative pass here, which is cool. And so we inside the create module right now, so we can start from front of house here. Okay. So the first time we call the add to waitlist function in eat at restaurant, we use an absolute pass. The add to waitlist function is defined in the same kernel as eat at restaurant, which means we can use the create keyword to start an absolute pass. We then include each of the successive modules until we make our way to add to waitlist. You can imagine a file system with the same structure. We specify the path front of house hosting add to waitlist to run the add to waitlist program. Using the create name to start off from the create route is like using // to start from the file system root in your shell. The second time we call add to waitlist in eat at restaurant, we use a relative path. So yeah, here we don't use the create module anymore and start from the front of house. So second time we call add to waitlist in we use a relative path. The path starts with front of house, the name of the module defined at the same level of the module tree as it at restaurant. Here the file system equivalent would be using the path front of house hosting add to waitlist. Starting with a module name means that the path is relative. Yeah, so basically we're already in the create folder, so we don't need to start from it. We can start something inside our folder. This is, yeah, clear to me. Choosing whether to use a relative or absolute path in a decision you make based on your project and depends on whether you're more likely to move the definition code separately from together with the code that uses the item. For example, if we move the front of house module and the eat at restaurant function into module named customer experience, we need to update the absolute path to add to waitlist. But the relative path would still be valid. However, if we move the eat at restaurant function separately into module named dining, the absolute path to the add to waitlist call would stay the same, but the relative path would need to be updated. Our preference in general is to specify absolute path because it's more likely we'll want to move code definition and item calls independently of each other. Let's try to compile and find out why it won't compile yet. The error will get it's shown in listing 7.4. So yeah, there is different strategy, and depending on what we are going to do and what we expect to refactor it, we can use absolute or relative passes. But I guess we will find our style from the practice part at some point. What is usually more practical for you or your team you're working with or the project you joined. I think this is kind of thing that happens if you can go different ways. Each team decide yourself how they going to handle this situation. And this one we actually already resolved. So by default everything is private, so we cannot access it. And if we run cargo build, we will get hosting private mode. So to fix it, we like to have a pub, and for function we need to pub as well. Sorry. So hosting is defined here. Model hosting is private. Model hosting is private. Basically, yeah. So the error message says that module hosting is private. In other words, we have the correct path for the hosting model and the add to waitlist function, but Rust won't let us use them because it doesn't have access to the private section. In Rust, all items, functions, methods, structs, enums, modules, and constants are private to parent module by default. If you want to make an item like a function or struct private, you put it in a module. So yeah, by default everything private. If you want to hide something, just put it inside the module. Completely makes sense. Item in parent module can't use the private item inside child module, but items in child modules can use the item in their ancestors modules. This is interesting. This is because child modules wrap and hide their implementation details, but the child modules can see the context in which they're defined. Okay. To continue with our metaphor, think of the privacy rules as being like the back office of a restaurant. What goes on in there is private to restaurant customer, but office managers can see and do everything in the restaurant they operate. Rust choose to have the model system function this way so that hides inner implementation details is hiding inner implementation details is default. That way you know which part of the inner code you can change without breaking outer code. However, Rust does give you the option to expose inner parts of child models code to outer center ancestor. Sorry, let me check. Ancestor. Code to alter ancestor module by using the pub keyword to make an item public. So exposing paths with the pub keyword. Let's return to the error in listing 7.4 that told us that hosting model is private. We want the eat at restaurant function in the parent module to have access to the add to waitlist function in the child model, so we mark the hosting model with the pub keyword as shown in listing 7.5. Okay, pub here and and we also will need to have pub here. We already found out it. So unfortunately the code in SNL still results in error as shown in listing. Because add to waitlist is private. So because there is no pub for function. What happened? Adding the pub keyword in front of mod hosting make the model public. With this change, if we can access front of house, we can access hosting, but the contents of hosting are still private. Making the model public doesn't make its contents public. The pub keyword on a module only let code in its ancestors module refer to it. No access its inner code, because modules are containers. There is not much we can do by only making the module public. We need to go further and choose to make one or more of the items within the module public as well. The error in listing 7.6 say that the add to waitlist function is private. The privacy rules apply to the struct, enums function and methods as well as modules. So the privacy rules apply to the struct, enum function and methods as well as modules. Okay. Yeah, I'm trying to think what it does it mean that the privacy rules. Basically, we cannot access something inside here. It's private. like if we create function here, but if we will make it public, not sure if we can access it anywhere, so maybe some example will help us to understand it. So let's also make the add to waitlist function public by adding the pub keyword before its definition in listing 7.7. Yeah, we already did it, and now the code will compile. To see why adding the pub keyword, let us use this pass in the add to waitlist with respect to the privacy rules. Let's look at the absolute and the relative passes. In the absolute pass, we start with create the root of our crates model tree. The front of house model is defined in the crate root, while front of the house isn't public because the eat at the restaurant function is defined in the same model as front of house. So eat at restaurant function is defined in the same model as front of house. Yeah, we are in root crate module, it's same. That is eat at restaurant and front of house are sibling. We can refer to front of house from eat at restaurant. Next, in the hosting module marked with pub. Okay. We can access the parent module of hosting, so we can access hosting. Finally, the add to waitlist function is marked with pub, and we can access its parent module, so this function call works. In the relative pass, the logic is the same as the absolute pass except for the first step. Rather than starting from the create root, the pass starts with front of house. Yeah, we skip this model because we already here, and now we can just call front of house. The front of house model is defined within the same model as eat at restaurant, so the relative pass starting from the model in which eat at restaurant is defined works. Then, because hosting and add to waitlist are marked with pub, the rest of the paths work, and this function call is valid. Okay. If you plan on sharing your library credits so other projects can use your code, your public API is your contract with user of your crate that determines how they can interact with your code. There are many considerations around managing changes to your public API to make it easier for people to depend on your crate. These considerations are out of the scope of this book. If you're interested in this topic, see the Rust API guidelines. Let's quickly look at it. Oh, it's so small. Let's make it bigger. So it's quite interesting. So there is naming, interoperability, macro documentation, predictability, flexibility, type safety, dependability, debuggability, future proofing, necessities. Okay, well, this is nice one when we will create our library first, maybe for public use. Yeah, to publish it, definitely something we need to go through. I think this is it's look like it valid points not only for the Rust itself but also for other programming languages, so it can improve us as a programmers generally. So yeah, one day we will be there. But now let's back to our section. So Best practice for packages with a binary and a library. We mentioned a package can contain both a src main rc binary create root as well as src librc library create root, and both creates will have the package name by default. Typically, packages with this pattern of containing both a library and binary creates will have just enough code in the binary crate to start an executable that calls code with the library crate. This lets other projects benefit from the most functionality that the package provides, because the library crate's code can be shared. This is, yeah, I'm just thinking about monorepo, and right now I'm working on React.js multi-project monorepo, and there is a need to share the code, and it sounds like something related. This is like you put everything in the library and you can just access in different binaries. So yeah, binary crates you can have as many as you want, but library usually is one in this. Yeah, I think I got this point. This is something like, imagine you have several websites, for example, one website for the customers, another website for the I don't know, inner manager customer support, but they both interact with same API on the backend and have a lot of code in common. So you can have this library, but the binary will be different for each of website, and the library is the good place to share your code. At least this is my assumption from what I read there. So the module tree should be defined in the src librc. Then any public item can be used in the binary crate by starting process with the name of the package. The binary crate becomes a user of the library crate, just like a completely external crate would use the binary crate become a user of the library crate, just like a completely external crate would use the library crate. It can only use the public API. This helps you design a good API. Not only are you the author, you're also a client. Okay. In the chapter 12, we'll demonstrate this organizational practice with a command line program that will contain both a binary crate and library crate. Yeah, good to know. We will get some practice through this book. Because there is already a lot of information that without the practice it will just dead in our memory. So starting relative passes with super. We can construct relative paths that begin in the parent module rather than the current module or the create root by using super at the start of the path. This is like starting a file system path with the two dots syntax. two periods, I guess it's called as well. Using super allows us to reference an item that we can know is in the parent model, which can make rearranging the model tree easier when the model is closely related to the parent, but the parent might be moved elsewhere in the model tree someday. Okay, basically another way to accessing depending on how it will be moved. So yeah, consider the code in listing 7.8 that models the situation in which a chief fixes an incorrect order and personally bring it out to the customer. The function fix incorrect order defined in the back of house model called the function deliver order, defined in the parent model by specifying the path to deliver order starting with super. And the interesting thing, it's not a public function, but because it's in same scope, back of the office and deliver order, and the fixing current order is a center of basically we have access to sync in the parent module. Yeah, I think this one is clear, so we can move forward. The fix incorrect order function is in the back of house model, so we can use super to go to the parent model of back of house, which in this case is create the root. From there we looked for deliver order and find it, success. We think that back of house model and the deliver order function are likely to stay in the same relationship to each other and get moved together should we decide to reorganize the create model tree. Therefore we use super, so we'll have fewer places to update code in the future if this code gets moved to a different module. So as I said, another strategy, but in reality you still might move it in different places, even you guess it will be moved together. So yeah, but I think it's not a problem. You can just change the path and that's all. Making structs and enum publics. We can also use pub to designate structs and enums as public, but there are a few details extra to the usage of pub with structs and enums. If we use pub before a struct definition, we make the struct public, but the struct fields will still be private. We can make each field public or not on a case-by-case basis. In listing 7.9, we've defined a public back of house breakfast struct with a public toast field but a private seasonal fruit field. This models the case in restaurant where the customer can pick the type of bread that comes with a meal, but the chef decides which fruit accompanies the meal based on what's in season and in stock. The available fruit changes quickly, so customers can choose the fruit or even see which fruit they get. Yeah, let's quickly try this one. I didn't copy it. And we have some error. Or we just need to restart our LSP. Cargo run. So cargo build. Yeah, I think we are fine. No error anymore. So let's take a look. We have a module back of house. There is public struct breakfast and public field toast string. Seasonal fruit is private. It has implementation public function summer, and it can, okay, for the summer we say that we choose the toast and said the fruit is peaches. So we set this kind of toast and meal toast. Yeah, we changed the toast here, but yeah. The next line won't compile if uncommented. We are not allowed to see or modify seasonal fruit that comes with the meal, and we of course uncomment it, and yeah, it's private field as we expected. Okay, I think I got it. Because the toast field is back of all breakfast struct is public in the it restaurant, we can write and read to the toast field using dot notation. Notice that we can't use the seasonal fruit field in the it restaurant because seasonal fruit is private. Try uncommenting the line modifying the seasonal fruit field value to see what error you get. Also note that because back of house breakfast has a private field, that struct needs to provide a public associated function that constructs an instance of breakfast. We've named it summer here. If breakfast didn't have such a function, we couldn't create an instance of breakfast in it at restaurant because we couldn't set the value of the private seasonal fruit field in it restaurant. So basically, yeah, we cannot create this struct. We need some function, like we cannot create the struct here in this eat at restaurant, so we need special function that has access to the scope of the struct breakfast, which will take care of creating the struct for us. Okay. In contrast, if we make an enum public, all of its variants are then public. We only need the pub before the enum keyword as shown at least in 7.10. Oh. Yeah, but maybe for enum set makes more sense. We won't have the like access particular item in enum. Let's quickly try it. Just clear cargo build. We're good. So yeah, we haven't set pub for SOP or salad, but just have pub keyword before enum keyword, and you see we can access it here. So because we made the appetizer enum public, we can use the SOP and salad variants in the eat at restaurant. Enums aren't very useful unless their variants are public. It would be annoying to have to annotate all enum variants with pub in every case, so the default for enum variants is to be public. Structs are often useful without their fields being public, so struct field follow the general rule of everything being private by default unless annotated with pub keyword. There is one more situation involving pub that we haven't covered, and that is our last module, system feature, the use keyword. We'll cover use by itself first, and then we'll show how to combine pub and use keywords. Okay, okay. Yeah, I think this is it for today. We did great job covering half of the 7th chapter. And my cat want to join as well. Yeah, but we'll continue next time with bringing paths into the scope with use keyword and separating module into different files. This will be finish of the chapter 7, and next chapter actually the command collections, which is quite interesting, I expect, at least it. So yeah, that's it. Thank you everyone. See you on the next stream.